We're going to talk parallel computing in this lecture. The background is that every computer today it has multiple cores, and some computers even has multiple CPUs in it, therefore more cores. However, most algorithms so far are single-threaded. They're not able to use all the cores available. Only parallel algorithm can take advantage of the resources and have a speed up. We're going to briefly discuss computational complexity, then we're going to use fixed point iteration examples to introduce parallel algorithms, and the computational complexity will be used to analyze how much speed up we may get out of those parallel algorithms. First, let's introduce computational complexity based on flop count. A floating point operation, or flop, is a single unit of arithmetic operation applied to a floating point number or pair of floating point numbers. Examples include addition, subtraction, multiplication, and division. There are some non-elementary functions such as exponential, logarithm, and square root. Although they may take multiple actual operations to implement, we only count them as a single flop. Let's use the Euclidean norm of an n-dimensional vector as an example. To calculate it, we have to do n self-multiplications of the entries, and then have to do n-1 additions among the entries, and then take the square root. So altogether, it costs 2n flops to compute, and we use big O notation to hide the constant and to describe how the flops grow with respect to the input size. Here are some examples of numerical linear algebra operations. Multiplying a n by n matrix to a n vector costs O and n flops. Multiplying two matrices, where the first one has m rows, n columns, the second one has n rows, p columns, costs O and p flops. To compute a times b times x, there are two ways. The first way, which is better, first compute b times x, which costs np, and then compute a times the resulting vector, which costs mn. If we first calculate a times b, then that step itself costs m and p. Then multiplying the vector, the matrix to the vector costs much less, but is dominated by the matrix multiplication. Given a square matrix with n rows and n columns, computing the inverse generally costs n cubed. Flop per second is a good indicator of the processing power of a CPU core or GPU core. Today, each CPU core can process roughly anywhere from half to several, like 6 or 7 gigaflops per second. That's a lot of number. So flops needed divided by the flops offered by the CPU core roughly predicts the runtime of algorithm on the CPU core. But this analysis is a very rough estimate because many issues like caching, like how memory communicates with the CPU, etc. So please expect a 10 or even 100 times inaccuracy. So this book and this lecture use both algorithm and method to describe how to implement a certain computational task. However, the two words sit at different levels of specifications. Methods is a higher level specification. It describes the computation in the mathematical equation and in iterations. Algorithms is a lower level of abstraction. It describes the step-by-step implementation of the method in the computer. To clarify, we can go even lower level by implementing an algorithm in a programming language. We don't go to that lower level. If an algorithm carries out the idea described in the method, we say the algorithm implements the method. So in a rigorous discussion, flop count is only ascribed to an algorithm, not a method, because a method may have different algorithms which have different flop counts. Consider the method that generates a sequence of x in this iteration, where A transpose of the parentheses is the gradient of the least squares of ax minus b. The algorithm corresponding to first computing a times xk, then subtract b, then multiply by a transpose cost OMN flop per iteration. That is the cost of the two matrix vector multiplications. By pre-computing and storing the matrix A transpose A and the vector A transpose B, the algorithm corresponding to this computation, which boils down to multiplying this matrix to xk and subtract the vector cost n squared flops per iteration. So which one is better depending on the comparison between m and n? To save words, we introduce this notation flop counter operator to denote the number of flops of an algorithm A used to compute the output given the input. Note that, again, the algorithm A is not the method that determines the flop count. However, when A is clear from the context, we may omit it from the notation. Here's an example. Given matrix A, to compute identity plus of A transpose A inverse can be decomposed into two steps. So the cost is the cost of the sum of the cost of the two steps. The first step is to compute the matrix that we are going to invert. The second step is to compute the inverse itself. The first step takes mn squared, which is dominated by the cost of A transpose A. The second step is n cubed. Together is O m plus n squared. Here's another example. Consider the lasso model, where the first part is least squares, the second part is lambda times the L1 norm of the unknown x. The Dollar-Rushford iteration has three steps. The first step is a proximal step with respect to the input. The second step involves the proximal with respect to the L1 norm, which boils down to solve the thresholding, which we have introduced in the previous lectures. The third step updates the variable. Using the flop count operator, we can express a naive implementation of this iteration. It boils down to four steps. The first step calculates the matrix inverse, and that is this part. The second step takes the zk, the current iterate, the computed matrix inverse A and B to compute, follow this line to compute xk plus half, and then third step are given xk plus half and zk, and follow this line to compute xk plus 1. The last step follows the last line. The cost of first step is already introduced in previous slide. It's m plus n squared. The second step the cost of second step is dominated by matrix vector multiplications, so which is m plus n times n. The last two steps are easier. They cost O(n) each. So the main cost of the dominating cost of this iteration is m plus n squared, dominated once again by the matrix inverse. We can reduce this cost by pre-computing the matrix inverse stored in memory and pre-computing the vector A transpose B with alpha multiplied and stored in memory. Then, at all the subsequent iterations, the per iteration computation boils down to using zk as well as the stored quantities in memory to compute the first DRS iteration, to compute the first DRS step, then compute the second DRS step, and then compute the third DRS step. And this is dominated by multiplying this matrix to the vector, which costs O(n) squared. So the total cost is dominated by O(n) squared per iteration. Next, we introduce parallel computing. An oversimplified view of parallel computing is that a group of computational agents working together, running concurrent control flows of computation to complete the same task. Depending on the context, agents may refer to CPU cores, GPU cores, or CPUs and GPUs, or even computers connected either locally or over the internet. Let's use an example to illustrate parallel computing, and our goal is to compute the sum of two matrices of same size, n by n, and assume we have P processors where P is less than m times n. Then roughly every processor is allocated this amount of m over n divided by P amount of flops to complete. And this can be expressed using this parallel for pseudocode. So for I equal to 1 through m, j equal to 1 through n, every entry Cij equal to the sum of corresponding entries. By parallel for, we means that the results of every iteration here does not depending on the results of any other iterations. Therefore, these steps can be carried out in parallel and in arbitrary order. We say a computational task is embarrassingly parallel if it's trivial to parallelize. So embarrassing here is a good word because little effort is needed. Besides the matrix addition example in the previous slide, we can also look at this example where we compute the matrix vector multiplication assigned to V. So we have parallel 4 over the entries of 1 through m. So we reset Vi and then sequentially add Aij times Xj to Vi. So that is to generate the ith row of ith entry of V. And these V entries can be generated in parallel. They do not depend on each other. Therefore, this part can be executed in arbitrary order. However, not all computational tasks are easy to parallelize. Consider the Douglas-Rutherford splitting iteration. The iteration has 3 steps. Every step uses the input of the results from some other step and the latest result from some other step. For example, the first step requires zk, which is the latest result of step 3 of previous iteration. The second step, xk plus 1, requires the latest results of the first step. The last step, zk plus 1, requires the later results of xk plus 1. So you have to complete a step before you can start another step. Therefore, these 3 steps have to be executed in serial. And also, when you apply DRS to actual application, usually the computational bottleneck lies in either prox of f or prox of g. If the bottleneck steps are not parallelizable themselves, DRS is not parallelizable. So we extend the flop count operator to parallel flop count operator with a little p there. It denotes the number of parallel steps that an algorithm A takes to compute the output given the input using p processors. The idea is that even though the algorithm has access to the p processors, it may or may not be able to process p flops at every step. Therefore, we need to analyze the number of parallel steps that it needs. We say an algorithm is parallel as long as it uses more than one computing units and it's serial otherwise. However, a method, this A is lowercase, is parallelizable if it has a parallel algorithm that can provide a significant speedup. Therefore, only if the parallel algorithm benefits from using P processors, we call a method is parallelizable. We say computing the output given the input is parallelizable if the parallel steps is much less than the serial steps. For some p large enough, the meaning of much less than depending on the context. However, a sufficient condition is that the number of parallel steps is roughly equal to a small constant times the number of serial steps divided by p. So the c should be much less than p. Then this computational task from x to y is parallelizable. Finally, we say an operator T is parallelizable if its parallel steps is much less than its serial steps. Reduction is a basic operation in many parallel algorithms. It is defined as combining a set of numbers into one number with an associative binary operator. The most common example is to compute the sum or compute the average, given n numbers. With p equal to 1, reduction cost O(n), and we hope with p greater than 1, the cost can reduce. With p greater than roughly n over 2, then the reduction takes O log n steps, where the base of log is 2. In the concrete example with n equal to 8 and 4 processors, the parallel steps needed to compute the sum is only 3, much less than 8. Specifically, we can assign a pair of numbers to every processor and ask them to calculate the sum, adding the 2 numbers together in parallel. So this is the first step. And the second step is to ask 2 processors to calculate the sum so that they get a sum of 4 in parallel. Now finally, we let the 2 processors with the 4 sum and doing addition to get the whole total sum. So as you can see, this follows a binary tree. When P is less than half the processors, The reduction cost breaks down to two parts. Let's use this example to illustrate the cost where n now increases to 40 and p stays at 4. So we first divide the 40 numbers evenly among all the processors. The 4 processors, every processor gets 10 numbers, and taking the sum of these 10 numbers take 9 steps, and that is local reduction within every processor. And this 9 steps corresponding to the first part. So after the sum are done, and then we can climb up the binary tree, which take log p steps. So to summarize, to compute the sum of n numbers, which is a typical reduction calculation, it's On if you only have one processor. If you have up to n over 2 processor, there's a serial part with n divided p, which is evenly dividing the work, and then there's a binary divide and conquer part, which is log p. If p is greater than n over 2, then the cost is no longer dependent on p, it's log of n. So likewise, we have other reduction operations, and the same results also apply to these operations. The first, the minimum and maximum of n numbers, those are reduction operations, and then also arithmetic mean, geometric mean, and the product of n numbers. There's some also calculations that are mainly depend on some reduction operations, such as inner product, which is pairwise product and then taking the sum. L1 takes the sum of absolute values, and L infinity norm takes the maximum of the absolute values. We can extend the results of reduction from inner product to matrix vector modification. So here we have M by N matrix and N vector X. We want to compute a matrix B with M entries. When P equals 1, of course, it's cost OMN. When P is less than M, we can distribute the entries of B to the P processors. So each processor roughly gets a M over P entries to take care of, and every entry requires an inner product of the corresponding row of A with the vector B, X. That takes that serial computation takes ON. So together, every process roughly going to take this number of flops. When there are more than when P is more than M, then some row is going to be assigned to do binary reduction, which is faster. So in that case, this is the serial part like before, and this is the binary reduction part. When P is more than Mn over 2, then every entry B is assigned to over n over 2 processors. So not only are the entries of B can be computed in parallel, each computation can also benefit from binary divide and conquer. So that gives you O log n. It no longer depends on the row. So here there's a missing division sign. So counting just the flops is a useful approximation to some runtime analysis. However, just knowing the flops is inadequate because, first of all, data have to be available for the parallel processors to take advantage of, and then different processors may need to communicate, which cause latency, data transmission time, as well as the coordination time, which can be significant. Modern GPUs have thousands of slower cores. They're very good at running the same program over thousands of data streams. However, coordinating different programs and running reduction operations can be slower. When we go distributed or decentralized, we're talking about computers that are connected in a local network or even the internet. In that case, the cost of communication becomes even more significant. It's good to know that a method may be parallelized in different ways. Say a method relies on linear algebra operations such as a times x. Because a times x can be parallelized, whenever it needs a times x, we parallelize this step. And this is called linear algebra level parallelization. In some case, a method itself is also parallelizable, as we will see in the second half of this lecture. It's also good to mention that sometimes a method needs to be run over different data. Therefore, the whole task is parallelizable at an even higher level, not involving parallelizing the method itself. Loading the different levels can help because they can be parallelized at different efficiency. Consider an optimization problem where f is CCP and there are m HIs where each of them is CCP and differentiable. Assume that m is relatively large. Let's try to find a parallel algorithm. Specifically, let's consider for backward splitting iteration, where we first compute the gradient of the differentiable part and then take the proximal step over f. Assume prox f cos cf flops greater hi for each I cos ch flops. Then calculating y iteration can be decomposed into 3 steps. The first step, calculating all these gradients, m of them. And the second step, combine these gradients into an average multiplied by negative alpha to give vk. The last step, just do this addition and then calculate the prox. The first step is parallelizable. Then because m is assumed to greater than p, so we can divide the calculation of these m gradients over the p processors. So we get m over p times ch. The second part, one approach is to parallelize it is to divide the n entries, since n is greater than p, divide the n entries over p processors and add each processor to sum those m items over those entries they get assigned to. The last step, there's a sum here, which is the same story, but we have to calculate the prox f, which is the non-parallelizable part. So altogether, we have 3 parts that are divided by p and the part that does not divide by p. The method is only parallelizable if Cf is approximately equal to or less than this quantity. Consider minimizing f of x plus the average of gi, where both f and all the gi's are CCP and approximable. Using the consensus technique, we can reformulate the problem into this form where we have m variables and a consensus constraint which requires all the m variables to equal one another, and the last part that are where every gi depends on individual xi. The Rushford splitting algorithm has 3 steps. The first step involving taking the mean of the zi vectors, then calculate the prox over f, and the second and third steps are applied for every I. And for every I, we first have to calculate the difference, then calculate the prox over gi, and then finally update the zi. Assume prox f cos cf, prox gi cos cg for every I, and p is less than or equal to m, and then updating all the zi variables has, again, similar to the previous slide, has decomposable parts which are parallelizable. We get mn over p and cgm over p, and prox f in general is not decomposable, so it's not parallelized. So this algorithm, this method, is parallelizable if cg is less than or equal to mn over p plus cgm over p. We consider minimizing CCP function of f plus the sum of CCP function gi of ai transpose x, where ai is an n vector, x is the n vector, minus scalar bi. Write down the Lagrangian, which is saddle point function, which is convex in f and concave in u. And then when we fix all the scalars u minimizes over x, and we can generate this dual objective function, where the first part is a single function convex conjugate of f, or f star, of a sum. Inside the sum, each ui is scalar, every ai is a vector, and the second part of the objective are decomposed as separable functions of ui's. Now, if we assume f is strongly convex, then f star is differentiable, is smooth. Therefore, we can take gradient of this part with respect to u, and then this part is proximable when gi's are proximable. So we can apply forward backward splitting to the dual because the first part of dual is differentiable. And then we're first calculating, given uik, we first calculate the sum, which is the weighted sum of ai vectors, and then calculate the gradient of the convex conjugate. Then for each I, we calculate the sum, and then apply prox gi star. So assume the gradient costs cf flops, and each prox gi star costs cg flops. Assume p is no more than m or n. Then the cost of updating all the dual variables breaks down to two parts. The first part is parallelizable part, and the second part, cf, is not parallelizable. Next, we look at the support vector machine formulation. So here, ai's and yi's are given. ai's are feature vectors, yi's are labels, plus and minus 1, and lambda scalar. And the objective is to find this vector n, which is a normal vector, normal direction vector of a hyperplane that are supposed to separate these numbers. The first part is differentiable strongly convex. The second part is not differentiable but still convex. And the second part has a summation over m, where m is number of data points. M can be big. Applying forward backward splitting to dual formulation of this problem can yield this, where we can first calculate x, which involves a summation over m data points, and then for every I, we calculate this quantity and project it onto the interval minus 1 and 0. When p is no more than m and n, this algorithm is parallelizable because the cost of updating all these dual variables is evenly divided by p. In the last part of this lecture, let's study Amdahl's law. Let's motivate this Amdahl's law using proximal gradient algorithm. Assuming the gradient step takes 6 milliseconds on one processor, and the proximal step takes 3 milliseconds on one processor. And suppose we're able to reduce the computation of the first step from 6 milliseconds to 0, but not able to reduce the time 3 milliseconds on the second step. Then speed up is 6 plus 3, which is the time before parallelization, over 0 plus 3, which is the time after parallelization. And this gives us 3. So 3 is the maximum speed up achievable by reducing only the computational time of the second step, but not the first step. So this means that even if we have lots of processors and we are able to very successfully reduce a proportion of the running time in the iteration to even 0, we're subject to some kind of upper bound dictated by the non-accelerated part. This phenomenon is captured by Amdahl's law. In Amdahl's law, suppose there's a computational task and eta proportion of this task can be speed up by a factor s. Then the total speed up the whole computational task is the serial time, which is assumed to 1, divided by the proportion that is not accelerated, plus the proportion that is accelerated. This formula is called Amdahl's law. Now, even if s is infinity, we still end up getting 1 over 1 minus eta, which is the upper bound of the speed up of an entire computational task. Now, this really means that it's only worth accelerating the part of the algorithm if it does occupy a significant proportion of the total runtime. That is only if eta is large. If eta is small, it's not worth the effort of acceleration. It's time to conclude this lecture. So we have studied computational cost of algorithm, including parallel algorithm using flops. Although only considering flops is inadequate due to data organization and communication can affect the running time, this framework based on flops is still very useful for analyzing running time of algorithms.